Hi everyone. Today let's talk about section 6.5, length of curves. The idea. The integral can be used to compute other geometric quantities besides area under curve. It can be used whenever you can break up a problem into sum of infinite number of infinitesimally small pieces. The arc length of the curve, this is the arc length formula. How do we get this formula? Okay, let's see. Suppose a curve C is defined by the equation y equals f of x. So this is the curve, right? And you can see we can use polygonal approximations to divide the interval into n subinterval. So for each piece, we can use a line segment to approximate it. And then we can add up the length of all of these line segments. And if we let n goes to infinity, then what happened? Well, that the length will approximate converge to the length of the curve. Okay, so how do we compute? So let's look at this guy. So this is the line segment. Okay, let me use a different color. Okay, so let's focus on this line segment. Oops, so sorry. I pressed something. Okay, so let's look at this line segment. Okay, so let's zoom in a little bit. So if we say this is like change of s, then this is change of x, this is change of y. So you see we have a Pythagorean theorem. Okay, this line segment is equals to square root of change of x squared plus change of y squared, right? So arc length is like the sum of all of this change of s, okay, as we sometimes call it the arc length parameter, okay? And this is the sum of the square root of change of x squared plus change of y squared. But you can see change of y, change of x, when change of x is getting close to 0, this is approximated by the derivative f prime of x. So that's why you have change of y is f prime of x times change of x, and now you can factor out the change of x squared. When you factor it out and move it outside of the square root, it cancels, and then we only have the change of x outside, and the inside it become 1 plus f prime squared. So that's why here we have we factor out the change of x, and then we only have 1 plus f prime of x squared, and then change of x outside. So this is exactly this formula, okay, when n goes to infinity. Okay, and because we're integrating a square root functions, you know there are a lot of functions we're not able to integrate and get a nice formula for it. Same thing with the square root functions. In general, if I give you any x to the 4th minus 3x plus 7, can you integrate this guy? No. Okay, so it turns out the problem that I asked you and you're able to solve it by hand and get a number, I can summarize into 3 types. What are the first type? First type is you can solve it using U substitution. Okay, that is like this example 1. Well, second type is like example 2. You can use the fundamental theorem of calculus part 1, and then you can create a complete square inside the square roots, so that you can cancel the square roots and then you can continue and integrate it. Okay, so this is the third type, and sorry, that's the second type. The third type is there is a magical 1/2 there. Okay, we will go over and see what is the magical 1/2 means. Okay, but the idea is you also can create a complete square inside the square root, so the square and the complete square cancel, then you can continue and integrate it. Okay, Yeah, with this presence of square roots, it really limits us to only limited functions that we're able to solve and get a nice formula for the indefinite integrals. Okay, so let's go through all these problems. Example 1, find the outline of the arc y squared equals x cubed between the points 1, 1 and 4, 8. Okay, so this is the same as y equals x to the... Oh, sorry. It should be 3/2 because we're taking square roots. Oops. 3/2. We're taking the square roots on both sides. And it passed through 1, 1 and 4, 8. Okay, so it passed through it. So we want to find the outline of this piece. Okay, remember, first steps, we want to compute the derivative. Okay, so this is the case many students confused because in solving this outline problem, it involved taking the derivative and also it involved taking the integral. So sometimes when you do both things in the same time, that you might get confused. So be careful with that. When we take the derivative of the power rule, we move the constant down in front and we subtract 1 from the exponents. So it becomes x to the 1/2. Okay, so the at length, my x goes from 1 to 4. Square roots of 1 plus the derivative square. And so it's 3/2 x to the 1/2 square dx. Don't forget your parentheses, okay? This is the outline formula. And 1 to 4, 1 plus 3 square, 9, 2 square, 4, x square root square cancel. We get x. Okay, so type 1, U substitution, it means you have a linear function in the square root. Then you can let u be the things inside the square root. Then du will be 9/4 dx. So far, so good. So this guy equals u of 1, u of 4. Be careful, 1 and 4, they are x bounds. And you want to change to u bounds. Square root of u. And so dx is how many du? Well, we both sides multiply by 4, divide by 9, right? So we get 4/9 du equals dx. So dx is 4/9, but you can put the 4/9 in front of the integral and you can put du there. Alright, let's continue. What's u of 1? Plug 1 in it. You get 1 plus 9/4. That's 9 plus 4, 13/4. Okay, my habit is I love to change to u bounds, and then after I finish integrate and I get a formula of u, I can put it there. If you want to keep the x bounds, after you do u substitution, make sure you plug in your x back and then plug your x values into the x. Okay? When I plug in 4, 1 plus 9 is 10. This is u to the 1/2 du. Alright, integral of u to the 1/2, you add 1 to it. So u to the 3/3 times 2. Evaluate from 13/4 to 10. Okay, what is that? Well, that's the same as 8/27. And then we plug in 10 first. Subtract, we plug in 13/4 to the 3/2. And that's it. You can leave your answer like this, or if you want to type it into the calculator, you can also do that. So far, so good. See, in this case, why we're able to solve it? Oh, because we get linear function in the square roots, then we can use u substitution to solve. So this is the first type we're able to solve the integral. Okay, so type 2. Fundamental theorem of calculus, part 1. So what is that? Let me use a different color. Okay, so we talk about we reviewed fundamental theorem of calculus part 1 in the first week of class. Okay, I hope you can still remember. So y prime is the dx of here 0 to x square root of 9 cosine t square plus 6 cosine t dt. Right? And remember, there are two things we need to check. First thing, you want to check whether the lower limit is a constant. Is it? Yes. Second thing you want to check whether the upper limits match with the dx in terms of in front of it. And yes. So if we satisfy those two conditions, we can simply, remember, we're not differentiating the function, we're not integrating the function, we just replace t by the upper limit. So same function, replace t by x. That's the y prime. And so at length, my x is from 0 to pi over 2 square root 1 plus y prime square. But can you see y prime square? Well, the square roots will cancel. So we only have, maybe let me write down the square root. So square roots square, they cancel. Okay, so, and then don't forget the dx. And then we have, when they cancel, we also can reorder it. So I can get 9 cosine square plus 6 cosine x plus 1. And can you see what happened? Well, this is actually a complete square. So what is complete square? Well, a plus b squared is a squared plus 2ab plus b squared. So 9 cosine squared is 3 cosine x parentheses square. And the 6 cosine x is like 2 times cosine x. And 1 is like 1 square. So this is actually the complete square of 3 cosine plus 1. See? Complete square, I can cancel with the square roots. So that helps us to get rid of the square root. Alright, see, now we're able to integrate. That's why I say type 2. We can use fundamental theorem of calculus part 1, and our goal is to get rid of the square roots. Okay. Next, integral of cosine. Then that is sine, right? Because the derivative of sine is positive cosine. Integral of 1 is just x. Alright, so we plug in pi over 2, and what is sine pi over 2? Well, sine function, remember, when it's pi over 2, we have 1. So this is, and when we subtract 0, sine of 0 is just 0. So we have 3 plus pi over 2. So this is our answer. So far, so good, everybody. All right, let's continue. The third type. Okay, magical 1/2. You see what this 1/2 means. Okay, so we want to find the at length of this function. And same thing, first step, we want to find the derivative. Many students realize they're not able to make a complete square inside the square roots. Well, that might be because they forgot to differentiate it. Okay, and maybe they make some mistakes when they differentiate. Instead of multiply it, they maybe divide the round number. So go back and check your work. Okay, so here we differentiate. Derivative of 2e to the x is 2e to the x. Derivative of that is minus 1 over 8e to the minus x. Right, so that is the derivative. And then integral x goes from 0 ln of 2 square root 1 plus the derivative square. So far, so good, everybody. Alright, let's continue. So this is one, or complete square is, so keep this in mind, a plus b squared is a squared plus 2ab plus b squared, a minus, well then you just change the middle term to be minus. Okay, so this is the 4, e to the x squared is e to the 2x, minus 2 times 2e to the x times 1 over 8 e to the minus x, plus 1 over 8 times 8, 64, e to the minus x squared is e to the minus 2x. Okay, now what happened? Do you see this term? 2, 2, and 8 is actually 1/2, and e to the x and e to the minus x cancel. So this guy is actually 1/2 because it's minus 1/2. So when we combine with the 1 minus 1/2, what is that? Is positive 1/2, right? So 4 e to the 2x, keep it there, and 1 minus 1/2 is another 1/2. So far, so good, everybody. Okay, now I want you to look at this integral more carefully. Look at these guys. Oops. And this guys. Remember the middle term is also 1/2, right? This guy is 1/2. Okay, what's the difference? Do you see the only difference is the middle term? One of them is minus, the other one is positive. So, you see, this guy will actually give us another complete square. It's almost the same thing as before, but right now you just change the sign from minus to positive. So, what is this guy? So, you know, this guy is exactly the 2 e to the x minus 1 over 8 e to the minus x squared. So change the middle sign by positive. See? You compare with this guy. So far, so good. This is the magical 1/2 because only 1/2 will work and you still get a complete square. Think about it. If it's not 1/2, let's say if it's 1/3, then 1 minus 1/3 is 2/3. So you don't get all the terms the same and the middle term only different by a sign. Or if it is not 1/2, if it's 1/4, 1 minus 1/4 is 3/4. So you get the numbers are different. So that's why this way, if you still want to get a complete square inside, that guy must be 1/2. So that's why I call this type magical 1/2. Isn't it magical? Okay, listen everybody, listen carefully. I know, okay, you're gonna expect if I make a problem in the exam, you kind of expect, okay, the middle guy should be 1/2. Then some of you just jump from this step to this step. Just erase the 1 and change the middle sign to positive. No. You need to show all your work. So you need to show this intermediate steps in order to receive credits. Even though you know the result is gonna be change the middle sign from minus to plus, but you still need to show all your work. Okay? Because maybe you make a mistake for your coefficients. You actually don't get 1/2. Okay? So everybody, you need to show your work to receive all credits in the exam. Okay, let's continue. So square and square roots cancel. So we have 0 ln of 2. So 2 e to the x plus 1 over 8 e to the minus x dx. Well, integral, oops, sorry. I pressed the wrong button. Okay. So integral of e 2e to the x is 2e to the x. Integral of that is minus 1 over 8 e to the minus x. Evaluate from 0 to ln of 2. So we plug in ln of 2. Then e to the ln of 2 is 2. 1 over 8. E to the minus ln of 2 is actually e to the ln of 2 to the minus 1. Ln cancel. So 2 to the minus 1 is 1/2. Minus, when we plug in 0, e to the 0 is 1, e to the 0 is 1. So 4 minus 1 over 16 minus 2 plus 1 over 8. 4 minus 2 is 2. Minus 16 plus 1/8 is 1 over 16, right? So this is 16. 32 plus 1, 33. 33 over 16. So far, so good, everybody. Don't forget to show all your steps in the exams and homework in order to receive all credits. All right. Okay, let's continue. Example 4. Find the length of the of this function. So I hope everybody can pause the video here and try to work on this problem first. What is the derivative? Constant multiple stay there. 7. Put it down. 7 minus 1, 6. And constant multiple stay here. This is the same as x to the negative 5. So what do? You multiply by negative 5 and then x to the minus 6. I strongly recommend you, before you apply the power rule, please write the function in the standard form. Because now you know it's x to the negative 5. Negative 5 minus 1 is negative 6. You're actually increasing the magnitude. The magnitude is from 5 to 6. It's actually increasing. Even though you're subtracting 1 because it's in the denominator. So the number actually increase in magnitude. Alright, 7 and 56, that's 1 over 8. 5 cancel, you get 2, x to the minus 6. So far, so good, everybody. And then, at length is from 1 to 2, square roots of 1 plus derivative square. Alright. Okay, so when we square it, first gotta square, so 1 over 64, x 6 times 2, 12, minus, okay, 2 times 1 over 8, x to the 6, 2 times x to the minus 2, minus 6, plus 2 squared, 4, x to the minus 12. Well, this guy cancel, 2, 8, we get 1/2. See? Magical 1/2. 1 minus 1/2 is 1/2. So this is 1 over 64, x 12 plus 1/2, and plus 4 x to the minus 12. Okay, remember what is this guy? This guy is, oops, let me use a different color. Okay, this guy is gonna be this guy, but change the middle sign from minus to positive. So we know that is 1 over 8 x to 6 plus 2x to the minus 6 squared. Now square and square root cancel, so we can integrate. Okay, what is the integral of that? We add 1 to the exponent, so x to the 7 divided by 7. Oh, so that give us 56. And then add 1 to the exponents, x to the negative 5 divided by negative 5. We get 2 over 5. So far, so good, everybody. Alright, and then we're gonna evaluate from 1 to 2. Okay, so what do we get? So we plug in 2. 2 to the 7 is 1 28 and minus 2 5. 2 to the 5 is 32, but it's actually in the denominator. Oops. Okay. So let me save first. Okay, and then minus, when we plug in 1, we get 1 over 56 minus 2 over 5. Okay. All right. And what is that? Well, so here we have a common factor 8. So we divide it by 8, we get 7, and that thing we divide it by 8, we get 16, right? So this is 7, we get 16. Oops. Okay. So that's 16 over 7 and minus, okay, 2 and 32, so it becomes, okay. There's something wrong with my computer right now. Okay, so, it's 1 over 5 times 60 minus 1 over 56 plus, it keep erasing my answers. Okay, so, and then we can put this in our calculator. So let's see, what do we get? 16 divided by 7 minus 1 over 5 over 16 minus 1 over 56 plus 2 over 5. So approximately equals 2.655 So far, so good, everybody. Okay. And so let's continue. So if a curve has an equation x is a function of y, and so we have the same idea, just simply replace x by y. So we have an integral with respect to y, and then we can take the derivative of x with respect to y. So we have dx dy instead of dy dx. Okay, so let's see this example. All right. So I will recommend you to separate them first. So separate them first. Okay, so let's see. It keep erasing my work. So okay, so let me see whether it work here. I think it freeze. So let me continue this example in part B. See you soon.